I'm very pleased to introduce the next speaker. I've known Tim Brecht, and we were just trying to figure that out since he arrived into the theory group in Toronto in 1989. And I was in the theory group in Toronto since a couple of years earlier, after doing his master's at the University of Saskatchewan. So we're continuing on the prairie theme. He then graduated about the same time I did, went to York University, and came back here as a professor in 1998, and has been here ever since. Last year he was awarded a Cheriton Research Fellowship, and he's here to talk about some of the work he's been doing since. There are many other things I could tell, ask me later, and we'll go from there.
And thanks, David, for the gift that allows me to get a Cheriton Fellowship, which is very nice. Thanks. So trying to figure out what to talk about today, it was kind of difficult. I could have talked about a bunch of different things, and ultimately I decided to talk about this because I'm very excited about this work. So it's joint work with Ali Abedi, a former PhD student who's now a postdoc with me. And the reason I'm excited about it is because we've discovered some interesting things and surprising things that are surprising and interesting not just to us, but to people who are building and selling Wi-Fi devices. And so I'm going to talk about what we've been doing. So the motivation for this work is that there's 3 billion Wi-Fi devices that are going to ship this year. By the end of the year, there's an estimate that there will be 9 billion devices in use. And some of this is caused by the growth in IoT devices. So we've got, and you'll see a box like this around. This is an access point, right? It's how you connect to the internet. Tablets, televisions, media players, console game boxes, and more IoT devices like this Wi-Fi enabled thermostat and a Wi-Fi enabled plug, right? That allows you to turn things on and off and monitor the power consumption. So all of this growth in devices it means that there's more growth in access points, right? So this is a recent, that's the recent number of access points I saw when I was at an airport recently, right? And if you, so there's a study that says that in developed countries, the median number of access points you see from your home is 20, right? So the density is increasing like crazy. There's more and more of these devices. And the big problem here is that Wi-Fi is a shared medium, right? So we're communicating over the airwaves using radio waves, and we have to somehow get these things all to work with each other. And so the other thing that motivates some of this work is that you may have spent maybe you've spent a lot of money through your ISP to make sure that you have high-speed internet connection through your internet service provider. And the studies have shown that in many cases, it's actually the Wi-Fi network and not the ISP that's the bottleneck. And so you may be paying for a high-speed ISP access, and your network may be limiting you. And the world is relying more and more on Wi-Fi devices for business and pleasure. So what makes Wi-Fi difficult and interesting? It seems really loud. Should I? I speak loud, so thanks. Thank you. So what makes Wi-Fi difficult or interesting, or both? Well, as I said already, it's a shared medium, right? So these devices need to cooperate with each other so that they're not sending at the same time. And then the other thing, and this is the part that we're really interested in, is this constantly changing channel conditions. And so I'll just give you some examples of what can cause channel conditions to change. So I've got an access point here, and maybe I'm sending some data or I'm receiving data, and I'm watching a hockey game on my iPhone, right? And if the thermostat decides to communicate, maybe it's sending data to the mothership so they can figure out whether the temperature should go up or down or whether I'm home or not, then those communications, those signals may arrive at the access point at the same time, and the access point may not be able to decode that signal. So it loses the data. The frame is lost. There can be interference from non-Wi-Fi devices. If there's a microwave in the vicinity and I'm using that spectrum, the 2.4 gigahertz spectrum or band, and somebody turns on the microwave, well, that causes signals that can interfere and, again, make it difficult to decode the data that's arriving at the access point or at my device. And then a third issue that's important is mobility. More and more these devices are mobile or portable, and we move around. So at this point, maybe I was sitting on the couch watching something or or downloading some data, and I've moved over to a different location. Maybe I'm now in the bedroom, right? And so that mobility also changes the channel conditions. It may be further away. It may have to traverse through walls, and so forth. Now, a lot of research has, it basically tries to avoid a bunch of these issues, right? They're really, really hard things to deal with. And so there's a bunch of research that gets done, not all research, but a bunch of research that gets done where they really work hard to try to avoid these kinds of scenarios. And so our work is really focused on how do we actually make progress in those environments in which devices are actually going to be used, right? So we've done some work on measuring Wi-Fi networks under changing channel conditions. We've built some trace-based simulation that, again, deals with mobility and interference of both the Wi-Fi and non-Wi-Fi variety. And the stuff I'm going to talk about today is about characterizing Wi-Fi networks. So the outline for the talk, I'm going to give a short outline because I'm going to spend a lot of time doing some background, and you're going to wonder, why is he telling me all about this background? It seems really boring. But the problem is that I need to give you enough background to tell you about what I'm going to talk about. So I'm going to talk about relationships between physical transmission rates. So first I'll give you a bit of background that you'll need to know to understand what physical transmission rates are and why they're important. And then I'll tell you about these relationships and then talk about how we're going to exploit those. So here's a bit of Wi-Fi background. So when a transmitter is going to send data, it needs to make a decision about what transmission configuration to use. So there are 4 possible things that it needs to deal with. So the first one is the modulation encoding scheme. So it has to select from, there are 8 varieties here, so from 0 to 7. The lowest number, 0, means that it's a low rate. And the reason it's a low rate is because there's a high level of redundancy is kind of a simplified way to think of it. So it's using extra encoding, so when the data arrives, it can be decoded quite well, but the amount of data that you're actually getting is pretty low. And so if the signal is poor between me and the access point, then I would use a very low rate and maybe have a high success of delivery. But if it's closer, then I might be able to use less encoding, a less redundant encoding, and get higher throughput. So there's an issue or a tension between picking the right rate that's high enough so I get high throughput, but a low error rate. Now the other thing to know about Wi-Fi, because this is a shared medium, if I send at a very high rate, then I occupy the airspace for a little period of time. But if I send at a low rate, I'm using more space in time, I'm using more time, and that means while I'm sending, nobody else can send. So if I'm sending at a low rate, not only am I running slow, but everybody else is hurt as well. So we'd like everybody in the network to send at a high speed as they can. So the first choice here, I've got 8 choices to make for the modulation encoding scheme. There's channel bonding, and so quickly and roughly speaking, you can think of it like this. Normally, I might have a 20 megahertz wide channel to send on. So this might be my house, and maybe my Wi-Fi device is using what's called channel 6. And your neighbor might be using channel 1, and they've got a 20 megahertz wide band to use as well. And now in order to increase speed, what the standards have done is they've said, hey, wait a minute, what if we bond these channels together? We create a wider channel, and now I can use all 40 megahertz to send. Now if I do that, and my neighbor's not using their Wi-Fi, things are going to be good. But if they are using their Wi-Fi, then maybe I'm not going to get as good performance. And so there's this choice that also needs to be made, which is, what's the channel bandwidth that I want to use? There's another choice to be made, which is whether we use short guard or long guard intervals. Roughly speaking, you can think of this as it's a little time space between symbols. And originally, this time space was chosen to be conservative. So it's fairly long, and that's called the long guard interval. And in recent standards, people thought, well, maybe we can be less conservative and make that a little smaller, but leave it up to the programmer, who's programming the transmission device, to make a choice between short and long. So by shortening that guard interval, you can see that the amount of time that's spent doing the guard interval is smaller, and we spend more time proportionally sending data, and so we get a little bump in throughput, maybe about 7%. But again, we're trying to get, the designers are trying to get every bit that they can. So that's another choice to be made. And then finally, the other thing that the new standards have worked on is being able to send again at high throughputs, and one way to do that is by using more antennas. So there's a choice to be made. These are called spatial streams. MIMO stands for multiple input, multiple output. And we refer them to them as simply as spatial streams. So in this example, I've got between 1 and 3. If I send with one antenna, I can send data through that one antenna. But if I use 2 antennas in parallel, then I can double my throughput, in theory. And if I use 3 antennas, in theory, I can triple my throughput. And so that's the parameter space. So when the transmitter is going to make a decision about how to transmit, it chooses between 8 MCS values, modulation encoding schemes, channel bonding, yes or no, or 20 or 40 megahertz, short guard, long guard interval, and then 3 possibilities for the number of antennas. So there's this choice of 96 combinations that it has to decide upon. What should it use in order to get good throughput? So we're going to use this notation to refer to these configurations. And so we have 1S is for one spatial stream, so I could have 1, 2, or 3 antennas, one way to think of it, 1, 2, or 3 streams. I have a choice of 8 modulation encoding schemes, so this could go from 0 to 7. Short guard or long guard interval. If it's a long guard, it'll be LG, and SG is for short guard, and then 20 or 40 megahertz for channel channel bandwidth or channel bonding. And then finally, we have, this ends up producing a physical rate. And so the physical rate is there just so you get a sense of, oh, okay, so this should be faster than the other rate. So this notation, we've chosen it so that we can look at 2 rates, like these 2 rates. If you look at those, they're really very similar, but they differ in one case, which is one's short guard and one's long guard interval. So where we're going with this is we're going to look for relationships. And the reason we're looking for relationships is that these 2 rates are very, very similar, except for the fact that one uses short and one uses long guard intervals. So maybe there's going to be a relationship between those 2 rates. And similarly, if I look at the next 2 rates, the bottom 2 rates, they're identical except for the modulation encoding scheme used. In one case it uses 6, in the other case it uses 5. And so maybe there's a relationship between those rates. Now, why are we doing this? Well, as I said, the access point has to make, or the sender, in this case the access point, has to make a decision about what transmission configuration to use. What rate should it use? So I'm going to show some data where time is going to move down here. And so maybe it sends at a packet or at a rate of 52 megabits per second using this configuration shown here. And so let's imagine that that works. And so the green indicates that that packet was successfully received. And so because it was successfully received at 52, it sends another packet at the same rate. And so it's moving along nicely, and maybe it's been doing this for a while. And then it says, well, wait a minute, right? If this works at 52, maybe I could do better, right? So the algorithm, the adaptation algorithm, so there's an algorithm that's built into the device that makes these decisions, tries 81 megabits per second. And let's imagine that fails. So that's what the red means, is that was not successful. So, well, maybe 81 was a little aggressive, so it backs off a little bit and it tries 72.2. And maybe that fails as well. So it backs off a little bit and tries 65, and let's imagine that that's successful. Okay. So this sending is trying to adapt because the channel conditions may be changing. So maybe at one point things were not working for this, or were working for this, and now they don't. Right? So these channel conditions change all the time. Microwaves go off, people are moving, people, not just devices are moving, but even people physically moving around in the room can change the channel conditions. And so this algorithm has to adapt in real time to try to meet and do a good job of optimizing sending for the channel conditions. So it was successful at sending 65 megabits per second, and so it does it again. It's thinking, okay, this is a pretty good rate. But now what happens is this phone is going to move. It gets further away from the access point. And now maybe the next packet sent, the encoding is not sufficient for that to be decoded at the other end, and maybe that fails. Okay. So now the device needs to make another decision about, well, what do I do now? Okay. So the reason we're interested, and these are what are called physical layer rates, right? So these aren't the application data rate. The application data rate might be 4 megabits per second for video, say, for example, right? But in order to get that there and not occupy the air time, we can send at a much higher physical rate. So at this point, the device knows something about the frame error rates of these different rates. So the frame error rate is, in this case, I sent 2 frames at 52 megabits per second, and they were both successful. So the frame error rate there is 0, right? I had 0 errors. I sent 2 packets, I have 0 errors, so the frame error rate is 0. In this case, I sent 1 packet, and all of them were not successful, so the frame error rate is 1. Frame error rate here is 1 as well. And in this case, I sent 3 packets, 1 failed, so my error rate is 1/3 or 0.33. Now imagine, and so this is where we're going with this, right? Imagine if, whoops, imagine if by knowing the frame error rate of this rate, if I could predict from that frame error rate the error rate of some other rates, then maybe I don't have to probe these. This is a probe, right? I decided I should try a higher rate because maybe that's going to work, and it failed. But if I could actually know ahead of time or estimate ahead of time my expected frame error rate for that rate, then maybe I don't have to probe that, and I could skip these 2 and go directly to that. Okay? So the question we're interested in, or the problem we're looking at today is, can the frame error rate of one rate be used to estimate the frame error rate of another rate? So in this example, right, if I know this frame error rate, could I predict these and just go directly to a good rate? And the reason we want to do that is because in an adaptation algorithm, we could reduce the number of probes, we could choose better rates more directly, and we could increase throughput. And there are other applications that maybe are a little bit tougher to explain right now, but in one case, we might be able to decrease our trace sizes. So I'm collecting a whole bunch of data. Maybe I don't need to store it all because I can infer it from some of the information that we know. So the definition of a relationship that I'm going to talk about here is it's a directional relationship. So the question is, can R1 be used to estimate, so that can the frame error rate of R1 be used to estimate the frame error rate of R2? And now, in this environment, there are 96 different rates. And I want to know, for all pairs of rates, does a relationship exist or not? Right? So that gives us nearly 10,000 pairs that we want to consider. Right? So I'd like to consider 10,000 pairs, and I'd like to do this in a way that, you know, Ali and I could take care of, instead of having to have, you know, millions of monkeys looking at these, I guess. And we also want to do this over extended periods of time. So here are 2 rates. I've got on the x-axis, I've got time. And so this is an experiment we ran, and we measured the frame error rates. So over time, so approximately 30 minutes of time, and these are the frame error rates. And I have 2 rates here, R1 and R2. And so you can see that as R1 changes, right, so it varies a lot over time, but as R1 changes, so does R2, right? And as R2 changes, so does R1. And so then the question is, well, is R1 possibly useful as an estimator for R2? And that's the question we're going to look at here. And it looks like they are, right? They're not the same, but there does appear to be a gap that's maybe roughly similar across the whole time frame, and so maybe there's a hope of doing some estimation. Now we want to quantify this relationship, so what we're going to do is we're going to take 2 points, R1 and R2, at one instance in time. So these have both been looked at over the same window of time. So in order to get a frame error rate, we need some window, right? And so we've got an error rate over some window of time here that produces a point on this graph. Let me back up a little bit. So with 10,000 of these, right? So if I've got approximately 10,000 pairs, what I could do is produce 10,000 of these graphs and look at them and say, yeah, that looks like a relationship. No, that one doesn't. Yes, this one does. And we didn't want to do that, right? So we're trying to boil this down to a single number that we can use on what we're going to call a heat map. So I'm going to produce a map that's that's got 10,000 dots, 96 by 96, right? So approximately 10,000. So I want to boil this down to, I want to take all of this information, boil it down to a single number that says, yes, this looks like a good estimator, or no, it doesn't look like a good estimator. So we take those 2 data points, and you can see here the frame error rate of R1 is about 0.4, and the frame error rate of R2 is about 0.6. And we're now going to put those onto a different graph. Okay? Now I'm graphing the frame error rate of R1 versus the frame error rate of R2. So there's 0.4 and there's 0.6, right? So that's that dot that comes out of those 2 data points from the previous graph, right? So I'm eliminating time from the equation now, right? So we're getting rid of time, and we're just looking at the relationship between frame error rate of R1 and R2. And now if you look at this graph, right, that's all the data points from the previous graph. If we look at that, yeah, there looks like there's probably a relationship there, just as we saw in the other graph. Now, how do we turn that into a number that we can deal with? Well, what we've done, or we've decided to do, is we've invented this notion called estimation power. So this is trying to quantify what we think the ability of R1 will be to estimate R2. How good an estimator will this be? Does it have good estimation power or bad estimation power? So the way we do this is we divide this up into bins. So each of these is essentially a 10% difference in frame error rate. So from 0 to 0.1, from 0.1 to 0.2, and so forth. And now, if we look in a bin, so this is one, what we're going to do is we're trying to figure out if I know the frame error rate of R1 is in this bin, right? So it's between 0.4 and 0.5. If it's in that bin, is there a likelihood that I can estimate what that value is going to be for R2? So we're trying to keep this simple and something that we can explain to vendors in a way that makes some sense. So what we do is we consider the dispersion, right? So if the dispersion here is small, then that probably means we can estimate it pretty accurately. If the dispersion is wide, then in that bin, for that frame error rate, we probably can't do a very good job of estimating. So our measure of dispersion, because these are highly variable in a wireless environment, we choose the 90, or an interdecile range. The way to think of it is throw off the top 10% and the bottom 10%, and then consider the range between what's left. So we have a bin, we compute some notion of dispersion, and if the dispersion is low, then we think that in that bin, that should work. And now what we try to do is to quantify for each bin that we have data for, then how many of those bins do we have good estimation power? So what I do here, so you'll see here, there's a check. So we have a dispersion threshold. Our notion right now is if the dispersion threshold is less than 0.2, so if the dispersion is small enough, i.e. 0.2, then we say that bin is a good estimator. If it's bigger than 0.2, in this case that's our dispersion here is 0.21, we say no, that's not a good estimator. And now to get a sense of, for the whole range of frame error rates, how good is R1 at doing R2, we count how many bins do we have low dispersion over the number of bins for which we have data, and then we get a value, in this case, 7 out of 8 of those bins have low dispersion, and so we say the estimation power in this case is 7/8. All right. Here's a different example. I've changed, so these rates, as we said, they differ a little bit. In this case, it's MCS index 6. In this case, it's 7. So they're very similar except for this encoding. If we make those slightly different here, this is now I8 instead of I7, and we produce a similar plot. We can see in this case I've got low dispersion here, but I've got very high dispersion here. So this range here is not a good estimator. And so if we look here, whoops, sorry. We've got 3 out of 8 bins we have low dispersion, and so our estimation power in this case is 3/8, which doesn't seem very good. So where I'm going to go with this is that we're going to run some experiments, and then what we want to do is produce a heat map to see where are there pairs of rates for which there is good good estimation power, and which ones don't have good estimation power. So this is, I should have a contest. So who knows where this is except for maybe people who live there? So this is the networking lab. So Ali used to sit here, Jim Summers used to sit here. So we set up an access point in the corner here. And the access point is sending data to that green star. Okay, so that's the stationary environment we're using. So this green thing is cubicles, right? This is a little private office. This is the hallway outside of the networking lab. So we're going to run experiments using 2.4 gigahertz Wi-Fi networks. And the 2.4 gigahertz Wi-Fi networks are being used so that we can see what happens when we have Wi-Fi and non-Wi-Fi interference. So there's a microwave next door in the PLG lab, a microwave across the hall. There are Bluetooth devices. And there are also 2.4 gigahertz networks being used and operated by IST. Right? So the students are using them while we're conducting these experiments. And then we built a 5 gigahertz network. We use the same devices. They're dual band, so we can run 5 gigahertz experiments. And those experiments are intentionally chosen. We use a channel that nobody else is using, not even the campus network, so that there's no, so that there's no interference. And the reason we want to see about no interference and compare this with interference is because we think maybe relationships will or will not exist depending on whether there may or may not be interference. So that's one set of experiments we run. Another set of experiments we run is mobile, right? So we have an access point here. Ali takes a laptop and he walks through the office area into the back room and then comes back and forth. And he repeats that for about 15 minutes. And then we do that for 2.4 and 5 gigahertz networks. And then we have a hallway experiment where we set up an access point in the hallway. And this mimics, people who are walking through the hall that you're bumping into all the time, right? Their heads down. It's like, excuse me. And so the idea here is we walk with the laptop away from the device and then back to the device. And we repeat that for about 15 minutes. And so now what we do is we're going to look at, are there relationships when we conduct these experiments between these different rates? So this is the 5 gigahertz office stationary environment. On the x-axis, I don't label them because the labels would be too small, but there are 96 different rates here and 96 different rates here. Each one of these dots is the estimation power. So if the estimation power is greater than 0.7, we think that that's a pretty good estimation power. So we color that in green. If the estimation power is between 0.5 and 0.7, that's medium. We color that yellow. And if it's below 0.5, we say that's poor, and we color that red. And so the shocking thing to us and the shocking thing to people at Google and Qualcomm that I talked to about this is that, oh my gosh, there's an incredible number of rates here, or of relationships here. And this is really kind of surprising. And so as I said, that's one rate there. Now, in some ways, when we thought about it a little bit more, and the other thing is this is over a 60-minute period, right? The channel conditions can change. And so if people move around, things are going to change. But yet these relationships persist, which was kind of interesting. But when we thought about it a little bit more, this is an office environment. It's stationary. So there's not, people moving can impact things. But there's no interference. And the other thing that's worth noting is that when we thought about it a bit more, it maybe wasn't so surprising that there were so many relationships because in this environment, lots of rates succeed 100% of the time, and lots of rates fail 100% of the time. And so it's pretty easy to predict from one rate that it doesn't matter what the other rate is doing. If the rate's always failing, I can predict that it's going to fail. It doesn't really matter. And so that's maybe what's happening here. So let's look at a 2.4 gigahertz experiment with Wi-Fi and non-Wi-Fi interference and with mobility. So what I've done here now, this is basically a 10,000 point graph approximately. What I've done is we've zoomed into one quadrant. So this is 1/16 of the whole graph. But again, the thing to note here is lots and lots of relationships. Okay, so there's lots of really potentially useful data here that we can use. So again, this was over 15 minutes. Now the other thing that's interesting here is that not only are there a lot of relationships, but there's one rate here. If I look here, this one rate, I can use that to estimate the expected frame error rate of every single other rate, just from one rate, right? So that one rate could be very powerful. So if I know that rate's frame error rate, then I don't have to probe those, right? I can guess, I can estimate what they're going to be, and I can decide whether that's a rate we're switching to or not. So what we've done is as sort of a proof of concept, right? We didn't spend a lot of time on this. We just said, let's find one simple relationship, and let's program that into an adaptation algorithm and see how much it helps. So what we did is we're estimating the frame error rate of the long guard interval rates from the short guard interval rates. There are lots of other relationships we could be using, but we're not. We're just using one simple one. And so that means that it's not that we're not going to use long guard interval rates. It just means that we're not going to probe them. So we're going to estimate what their frame error rate is going to be from the short guard interval rates. So we've modified on the device driver, we've modified the rate adaptation algorithm so that it can either not use, that's the vanilla case, not use our relationships, or use the relationships. So the purple bar is not using the relationships, and the green bar is with the relationships. And so just using these simple relationships, we're seeing improvements of 28% throughput here and 18% improvement here. This is a stationary environment with a 2.4 gigahertz network, and that's the mobile 5 gigahertz network environment. So it seems like it could be promising. And so now I'm going to switch gears and talk a little bit about how do we get to a point where we can apply this more widely. Like, this is a one-off hack just as a proof of concept. So there are these relationships, right? And I showed you in one case that one rate can predict all the other rates. So an interesting question is, how many rates does it take to be able to predict all other rates, right? So this is called a set cover. If we have a set of rates that covers all the other rates, that's a set cover. In this case, I've got rate 1 covers the set of those 4 rates. And let's imagine R5 covers those rates and R96 covers the remaining rates. So that's a set cover. Right? Covers all the rates. And then the other question is, what's the minimum set cover? So what's the minimum number of sets that I need to cover all of the other rates? What's the minimum number of rates? What's the smallest set of rates to cover all of the other rates? And so the idea here again is if this rate cover is, or if the set cover is small, then that means I have a small number of rates that I need to know frame error rates for, or sample or probe in order to calculate or estimate frame error rates of all the others. So what we did is we ran some brute force algorithms to find minimum set covers. And we found in that office environment, over that 60-minute period, the minimum set cover was of size 7. And we had seen this one already. It was size 1. This was size 1. In this case, it was 3, 2, 3, 2. So the amazing thing is that these set covers are really small. The minimum set covers are really small. Another question we have is, do these change over time, right? The channel conditions change over time, so we'd imagine that maybe these set covers change over time. So we took this 60-minute interval, and we chopped it up into 15-minute chunks. And we computed the set cover over the first 15 minutes, which was 3. The next set cover over that 15 minutes was 7, 5, and 1. So this size of the set cover changes over time. We're not yet sure, our next step of research is to see, does that really impact the relationships in a big way? But again, some interesting questions to look at. The other thing that we've done very recently, like just within the last couple of weeks, is that we wondered is there a set cover that I could use or find that's going to cover all of those scenarios? Right? So the idea is, if I could find a set cover that covers all of those scenarios, then maybe I could use that in a device. And let's go even crazier. Let's wildly dream. Let's imagine there's such a thing as a magic set. Right? So a magic set is, I find one set of rates, and I program that into my box, into all boxes, all access points, and that just works forever, for always. Right? I don't think that such a thing will exist, but that's something that we want to explore. And in fact, we found 152 of these, right? So there are lots of sets of size 7 that cover all of these scenarios. And this is really surprising. So I haven't yet talked to Google or Qualcomm about this, because this is something we just discovered. But this is surprising because there's lots of differences across these scenarios. We've got 2.4 gigahertz networks and 5 gigahertz networks. We've got interference and no interference. We've got stationary and mobile. We've got 2 different types of devices, right? In one case, it's a desktop device with PCI. The other one is a laptop USB. Receivers have different receiving properties. And so it might be the case that maybe receivers are different, but we've got some evidence that says, well, for two devices, maybe they're not so different. So the current research, so some potential questions and implications, as I talked about this magic set. Is there such a thing as a magic set? Or is it the case that if we do this in a home environment, so we've just done this in an office environment, but if I set this up in my home, do I have a different set? Do I have a different set of set covers that work? Or can we find one set cover that covers all scenarios for different homes, for different offices? So if that's the case, then I might be able to program this into an AP and send it out into the world, and we're done. Now, like I said, it's not clear. I don't know that we imagine that there is such a thing as a magic set, but maybe if there isn't, maybe there's just a calibration phase that needs to be done for the office environment in this case, or in a home environment. So you bring your access point in, you plug it in, it runs a discovery phase to discover relationships, and it remembers those and then uses those over time. Now, if that's the case, how and when and why would relationships change? If I'm at home and I'm using my access point and you come over with your device, do I have to recalibrate for your device, or does the calibration that's been done for my devices work with your device, for whatever device that is? And then the other thing we're working on is some estimator functions, right? Right now what we've shown is that there are relationships where we think that there's good ability to do estimation, but we haven't evaluated how do you come up with a function that does the estimation, and then how well do those estimation functions work? And then I guess another question is, well, do they even need to be accurate? Maybe they don't need to be very accurate to work well. So in summary, what we've been working on is characterizing relationships between 802.11 rates. We found that there are strong relationships between a ton of rates. So quite surprising, quite interesting, quite exciting. All rates can be estimated by a small number of rates. Again, that's very promising, very exciting for the 7 scenarios that we've examined, right? We need to examine more scenarios, and that's some of the research we're starting on. The simple use case that we've done shows that we could increase throughput in one example by 28%. Again, we think that there's a lot more potential there if we use more and richer relationships. So in future work, we're considering more applications of this work. It seems like maybe there's some possibility for doing some optimizations in mesh networks. We want to better understand the relationships. I think when we first started this work, we thought what we would do is try to understand relationships between MCS values, right? So if I have the same MCS value with 1, 2, and 3 antennas, is there a relationship there or not? But the fact that there were so many relationships caught us by surprise, and we haven't had a chance to do a deeper dive on those relationships. Now, the other reason that this work is interesting and exciting is because we're using a pretty old network, right? It's an 802.11n network. It's widely used, like 50% of the people will be using 802.11n networks today, but a lot of people are trying to use AC networks, right? AC networks have 640 rates. Right? So 640 that you've got to choose from. That means more probing, more potential poor performance, right? And harder decisions to be made. And the proposal for 802.11ax, which comes after AC, and I'm not sure that should be maybe 2019 or somewhere in that time frame, there's more than 1,100 rates. And so the hope and the belief is that by trying to understand relationships between these rates, we can do a much better job in existing and future networks. And that's it. Thank you.
Wow.
Was that okay?
That's amazing.
Okay, good.
Tim brought us back on time.
I forgot to...
No, perfect. Are there any questions? We have time. Jonathan.
You gave, of course, just very preliminary looking around, but one thing that you talk about is there any sense that if you look at the 4 different dimensions of change possible, I mean, is it that predicting when we change one dimension is more likely than predicting when you change 2 dimensions? I mean,
yeah, and so in some sense, though, I'm not sure if this is exactly what you're asking, but you can see there are some patterns here, right? And so those patterns, in a sense, are changes in dimensions. Now, some of it depends on the ordering that we have here and the ordering that we use here. But you can imagine that if so this is the goal next, is to start to look at these patterns and to see, if I change this dimension, how does that change the relationships, or does it change the relationships?
Yeah. Along those lines, one thing I see from this particular chart as it's placed up, there are, I think, 3 cases where the entire column is green. and those are close to, if not identically, to very high rates. So it seems here that trying for a high rate is very predictive of what would happen if you use less.
Yeah, so I find, so this one, at least from what I've been looking at so far, it seems like these middle rates are pretty good. So we've got 2 antennas. They seem like pretty good predictors of what's happening. What surprises me here is that these rates, which are the higher rates in this space, are pretty good predictors here as well. That seems a little funny to me. Now, yeah, yeah. Yeah, there are higher rates than these, because this is 1/16 of the total dimension, right? Yeah. Yeah, good point. So these are actually middling rates, right? So it goes up to 450, and these are, you know, in the 200 range. So yeah, so really they're high in this graph, but in the big picture, 10,000 dot graph, they would be middle rates. If that makes sense.
Any other questions?
Thank you. So one question I have is that when you define the relationship between 2 different rates, so do you also take into account the channel condition in that case? Like
The channel condition?
Yeah, because
Yeah,
the estimation can be different for 2 different conditions,
Yeah,
right?
I think that's what's surprising here,
Yeah.
right? Is there's no notion of channel conditions here, right? We conduct an experiment over time, and I think the thing is that the power of these relationships is that they seem to exist irrespective of the channel conditions, right? So the channel conditions can change the frame error rate for one rate, but it looks like maybe they're changing the frame error rate of another rate, or not changing the frame error rate of another rate in a way that's predictable.
Are there any further questions? David?
So moving a little afield from the specific thing you were doing, to me, particularly when you get up to the over 1,000 rates in AX, that seems kind of absurd.
Yeah.
Can you use this sort of analysis to conclude that there are just too many combinations and some of them maybe it's really just not worthwhile even to have as options?
Yeah, and that's one of the things that we think is where some of the value in this work might come in, right? So if you're a rate adaptation algorithm and you got to consider 1,100, if we can say, look, you know, probably there's 100 you need to worry about, then that would be great. And by the way, these are the 100, right? So that would be a nice situation. Yeah, exactly. Thanks. Originally, I think we were thinking maybe we could influence standards makers, but there are people who are trying to build, you know, really fast networks that work under all conditions. So I think they're going to do what they do.
Dave?
So you have these sort of super predictor
Yeah.
columns, but just stepping back for a moment,
Yeah.
I mean, if A can predict B and A can predict C,
Yep.
but you're saying B can't predict C, do you
Right.
want to just at the high level, why isn't the transitive property kind of happening? Is it an
Oh,
artifact
yeah,
of
let's
your?
see.
Is it an artifact of your binning? Is it
No, let's
like
see.
if A and B are correlated?
Yeah, no, I
and-
totally get
and
the
A and
question.
C
I
are
think I've-
correlated. Why aren't B and C?
I've got a slide for this, but let me see. Yeah, here it is. Oh, now you don't get to see that. How wonderful. Still not? Seriously? Let me see. I'm just trying to think, is there somewhere I can draw?
And I guess, well, part of it's related to is the correlation. So when you had the original where you're showing one rate versus another rate, that was happening at the same time?
Okay, here. Oh, crap. Okay, one more time. Sorry.
Yeah, it's a Mac.
Okay. Oh, okay. So
So go to your noisy graph.
hang on one second.
Yeah.
I'll answer the first question
Sure.
first, since I went and unhid that now. I think this might be what will do it. So here, I've got two rates. So this is the directionality of these, right? So this is a rate here. And what I have is this rate is failing all the time. The other rate, right, succeeds sometimes and fails sometimes. So the ability to predict here is very poor, right? So because that one experiences error rates all over the map. Now, if I flip these, right, then actually this rate, the rate that was on the y-axis is now on the x-axis, and it can predict with high accuracy the other rate, which is a little bit strange in some ways. So the problem here is that from the data that we have, right, so all we can do is get data that we have, right, and this rate never ever succeeded in this environment for this experiment. It never succeeded. And so all we have is frame error rates of 1. So every rate fails, but the other rate succeeds sometimes, and it fails sometimes. So here the dispersion is so high we can't predict that. And now here, though, when we flip it, it's just the other relationship from this rate to that rate. This rate is a very good predictor of that rate because it doesn't matter what the frame error rate is here, it's always 1. Right? So I can predict that pretty easily.
So with that, I think we'll give Tim another round of applause.
Okay, thank you.
Thanks for a great talk. And the new innovation this year is that even the locals get gifts. So
Awesome.
Awesome. There we go. Okay.